Hi everyone. Today we're going to be talking about the first target in Unit 4, which is being able to find work and power using equations or graphs and understand how that relates to energy. Specifically in this video we're going to focus on finding work using equations. So in order to do that, the first thing we should do is we should talk a little bit about what equations we can use to find work. And there really are two equations that we can use to find work. They look very similar, but there's some slight differences. For example, in this first equation over here, we've got the equation that work equals force parallel to displacement. And in our other equation over here, we've got the equation that work equals force times displacement times cosine theta. So let's talk a little bit about what those two equations mean. On the left equation, what it's really saying is that we're going to multiply displacement by the component of force that is parallel to the displacement. And then on the equation on the right, what we're really saying is that we're going to multiply the entire force vector by the entire displacement vector. And then we're going to multiply that by cosine of theta, where theta is the angle between the force vector and the displacement vector. We'll look at an example here, and we'll use this example to better understand how to apply those equations and how you would apply one equation versus the other, how they compare to each other as you apply them. So let's say we've got this scenario down here where we've got a box on a surface, and we've got the mass of the box is 4 kilograms. There's going to be an applied force of 20 newtons at an angle of 30 degrees above the horizontal. And then let's say that the kinetic coefficient of friction is 0.2, and let's say that this applied force is going to move the box 6 meters in the positive direction. Okay? So let's draw our free body diagram with these forces, and there's our force gravity, our force friction, and our force normal, and force applied. Notice that I made force normal shorter than force gravity, and that's because force applied is going to have a component in the upward direction, which together this y component of force applied and the normal force will balance out force gravity. So as a result, the normal force is smaller than gravity because the y component of force applied is helping it balance out gravity. All right, let's calculate some values for these forces. So force gravity is the mass times the gravitational field strength, and that comes out to be 39.2 newtons. The x and the y components of force applied are going to be the magnitude of force applied, which is 20 newtons, times cosine of 30, and 20 newtons times sine of 30. So there we've got our x and our y components of the applied force. Force normal is going to be working with this y component of the applied force to balance out force gravity. So the normal force is 29.2, because that, when we add that with 10, we get 39.2 newtons. And finally, force friction kinetic is mu times force normal. The normal force we know is 29.2, so multiply that by the coefficient of friction, and we get 5.84 newtons. And let's draw the direction of our displacement vector, because we know that we are going to want to be multiplying and comparing the directions of our force vectors and our displacement vectors when we calculate our work values. Okay, so let's go ahead and do this. Let's find the work done on the box by each force, and that way we'll practice using both of our work equations. So let's see. Let's start off by finding the work done by force gravity on the box. If we use our first equation, then what we notice is that force gravity points down, displacement points to the right. So if we're multiplying displacement by the component of force that is parallel to the displacement, then what we notice is that they're completely perpendicular. Force gravity points down, displacement points to the right, so they're not parallel at all, which means the work done by force gravity is 0. If we apply the other equation to this, then we're going to multiply force gravity times the displacement times cosine of the angle between force gravity and displacement. And the angle between force gravity and displacement is 90 degrees. And cosine of 90 degrees is 0. So when we multiply those things out, we find that the work done by force gravity is 0. And you're going to see as we do this for all the 4 forces that are acting on this box, we're going to find that we get the same value for work for each force, no matter which method or which equation we use. And that's a good thing, because you should be able to understand both these equations, and you should be able to understand how to apply each one in its own way. So let's now do the same thing for force normal. And actually, we're going to find that force normal is going to have the same results as force gravity, because force normal is perpendicular to the displacement vector. And as a result, they're not parallel at all, and so there's nothing to multiply together, and so we find that the work done by force normal is 0. And the way this plays out using our other equation is that when we are going to multiply the two forces, the force normal by the displacement, and we're then going to multiply that by the angle between them. And once again, they're perpendicular, so the angle between them is 90 degrees, and the cosine of 90 degrees is 0, so there's no work done by the normal force. Force gravity and force normal are doing no work, and that makes sense because they're both perpendicular to the direction that this is moving, right? The direction the box is moving is this way, and since they're perpendicular, they're neither helping move it in the direction it's moving or hindering the box's movement in the direction it's moving. So they're not doing any work. They're not giving work to the system or transferring work energy into the system. Neither are they transferring energy out of the system. All right, let's look at the more interesting forces, like force applied, for example. Force applied is interesting, and we see that part of it is, in fact, parallel to the displacement vector. The x component of our force applied is parallel to the displacement vector, and that's what we want to multiply together. So we take that x component, 17.32 newtons, and we multiply it by the displacement, which is 6 meters, and we find that the work done by force applied x is 103.92 joules. And I should really add a positive sign to that because it's doing positive work, meaning it's transferring, the force applied is transferring energy into the system. So for example, if a person is pulling this box, then that person is transferring their chemical energy into the box, or giving it to the box. So they're transferring energy into the system of the box. Let's see that we can get the same result using the other equation. With the other equation, we're going to multiply the total force applied by the total displacement, and that's 20 newtons by 6 meters. And then we're going to multiply that by cosine of the angle between those two. And we know that the angle between the applied force and the displacement is 30 degrees. So we are going to multiply it by cosine of 30. And sure enough, we find that we get the same answer either way. And that, you know, like I said earlier, is part of the point of this, is that you need to be able to use and understand this equation for work and this equation for work, and be able to know how to apply them, and they're similar in different ways. Finally, let's take a look at the kinetic force of friction. And we'll apply the first equation again, and we see that the force of friction points to the left, and the displacement points to the right, so those are completely parallel. But you might say that they're anti-parallel. In other words, one points one direction and the other points the other direction. So we can multiply the entire force of friction, 5.84, by the entire displacement. We don't need any components. And when we multiply those two things together, we get 35.04. But here's where this gets a little tricky. Because they point opposite directions, they're parallel, but they're anti-parallel, which means we need to add this negative sign. So it's actually, force friction is doing negative 35.04 joules of work on the box. And that makes sense because the negative sign tells us that it's taking energy out of the system. Friction is essentially taking energy away from the box, slowing it down. And it's going into thermal energy, but it's taking it away from the box. Finally, let's see that we get this same result when we use the other equation. And when we do that, we use the entire force of friction and the entire displacement, and we multiply it by cosine of 180. However, cosine of 180 degrees is -1. And so this negative sign comes from that cosine of the angle. And that's where this is a little bit tricky with the first equation. The first equation is tricky because if you multiply two vectors together, like a force vector and a displacement vector, and they're anti-parallel, meaning they point opposite directions, you are in charge of adding that negative sign and recognizing that that force is hindering the movement of the object, and therefore it's taking energy out of the system, and therefore you want to add the negative sign in because negative work is being done. All right, that is all for the first part of Target 1, thinking about and understanding how we use the work equation. I hope that was helpful. See you next time.